The life cycle of a star, with a mass between 8 and 20 times that of the Sun, always culminates in a spectacular explosion known as a supernova. Following this colossal event, octillions of tons of superheated plasma are hurled into space, rapidly expanding outward from the epicenter at speeds approaching that of light. This cataclysm releases an immense amount of energy in the form of light and neutrinos. At its very core, an extraordinary, compact object forms, composed almost entirely of neutrons and possessing incredible mass. A neutron star. Its properties are so extraordinary that they have occasionally baffled even seasoned astronomers, some of whom once entertained the notion that such phenomena might involve extraterrestrial intervention. At the critical moment when the core of a massive star reaches its limit, internal processes accelerate dramatically. Within mere thousandths of a second, silicon fuses into iron. However, under its own immense gravity, the core begins an irreversible collapse. Though this process lasts only fractions of a second, it triggers a cascade of remarkable phenomena. In less massive stars, the core is supported against further compression by electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed closer together. Yet if the core's mass exceeds 1.4 solar masses, the Chandrasekhar limit, even this powerful resistance proves insufficient, and collapse continues. Under unimaginable pressure, something extraordinary occurs. Protons, electrons, and other subatomic particles collide and merge to form neutrons. Almost all particles undergo this transformation. Once the core compresses to a diameter of roughly 20 kilometers, it becomes a dense sphere of neutrons, interspersed with a few protons and electrons, and surrounded by an outer layer of ordinary but extremely compressed matter. At this point, a new effect comes into play: neutron degeneracy pressure. Like electrons, neutrons strongly resist compression, but this pressure is vastly stronger than electron degeneracy. If the core's mass remains below approximately 2.8 solar masses, the Tolman-Oppenheimer-Volkoff limit, the collapse halts abruptly, encountering insurmountable resistance. This sudden stop generates an immensely powerful shock wave, which, combined with a flood of high-energy neutrinos, propels outward, triggering the star's explosive demise. Once the cosmic dust settles, what remains is a neutron star, one of the most enigmatic objects in the universe. It packs more mass than our entire Sun into a sphere no wider than a small city. To grasp the sheer scale of this phenomenon, consider this. The Sun's mass is 300,000 times greater than Earth's. Now imagine that entire mass compressed into a sphere the size of a modest metropolis. If that still seems abstract, consider another perspective. Most of the mass in any ordinary object, including the human body, is actually empty space. Each atom consists of a tightly packed nucleus of protons and neutrons, orbited by electrons moving at incredible speeds. If an atom were enlarged to a diameter of 100 meters, its nucleus would be no larger than a small marble. The vast emptiness between the nucleus and electrons defines the structure of normal matter. In a neutron star, however, all that space is filled with neutrons. Every particle is packed as densely as atomic nuclei, giving neutron stars their astonishing and unique properties. Prepare to be stunned by numbers that might make you sit down. The density of neutron stars is mind-boggling. A single cubic centimeter of neutronium, the material composing a neutron star, weighs about 400 million tons. To put this in perspective, that's equivalent to the combined mass of all cars, both passenger and commercial, in the United States. Imagine compressing 200 million vehicles into a sugar cube-sized volume. That's neutronium. Its density is so extreme that, from its perspective, ordinary matter appears as little more than a slightly contaminated vacuum. If a piece of neutronium were placed on Earth, it would sink straight through the planet. Any object this dense exerts unimaginably strong gravity. A person standing on the surface of a neutron star would be instantly crushed to a thickness of just a few atoms. This is due to the star's surface gravity, which is roughly 100 billion times stronger than Earth's. For example, a 77-kilogram person on Earth would weigh 8 trillion kilograms on a neutron star, 23,000 times the weight of the Empire State Building. But there's more. As any introductory astronomy course teaches, when a spinning object shrinks, its rotation speeds up, a principle exemplified by a figure skater who pulls their arms in and spins so rapidly their motion becomes a blur. The same happens to a stellar core collapsing into a neutron star. Before the supernova, the core might rotate once every few weeks. But once compressed to a 20-kilometer diameter, the newborn neutron star can spin several times per second. Its magnetic field intensifies dramatically as well. While a star like the Sun has a magnetic field comparable to Earth's, the collapse amplifies this field enormously. A neutron star can possess a magnetic field trillions of times stronger than the Sun's, so powerful it could erase the data on every credit card within 100,000 kilometers. Impressive, isn't it? These extraordinary characteristics naturally raise a question. Can such objects truly exist? The answer is yes. The first neutron star was discovered in 1965, though its nature wasn't fully understood at the time. 2 years later, another was correctly identified as a neutron star. But the story took a curious turn in 1967 when graduate student Jocelyn Bell, working on a radio telescope, encountered persistent, unexplained signals in her data. Night after night, she analyzed the patterns and eventually realized they weren't technical glitches, but emissions from a real astronomical object. Thus, the first pulsar was discovered. So, what is a pulsar? Pulsars are a type of neutron star. Their rapid rotation, combined with an immensely powerful magnetic field, causes them to emit two beams of energy, much like a lighthouse. As the star spins, these beams sweep through space. From Earth, we observe this as regular pulses or flashes of brightness, detectable in visible light, radio waves, and even X-rays. The rotation of a neutron star is so stable that these pulses function like incredibly precise cosmic clocks. In 1967, scientists couldn't believe a natural object could produce such regularity. The object was jokingly nicknamed LGM-1, Little Green Men 1. Today, We know of over 1,000 pulsars in our galaxy alone. We understand they are the collapsed cores of massive stars that survive supernova explosions. Some rotate once per second or even per minute. Others exist in binary systems, orbiting a companion star. If close enough, the neutron star can pull matter from its partner, which transfers angular momentum and speeds up the pulsar's spin. Some, known as millisecond pulsars, rotate hundreds of times per second. If they spun any faster, centrifugal force would tear them apart, despite their immense gravity. Even after 1,000 years, a pulsar remains a formidable cosmic force. At the heart of the Crab Nebula lies a pulsar, the remnant of the star that exploded to create this supernova remnant. Most of the nebula's light is powered by the pulsar. Its terrifying energy energizes the surrounding gas, causing it to glow brightly even a millennium later. Admittedly, the very idea of neutron stars inspires awe, especially before we even mention magnetars. Neutron stars aren't just strange balls of neutrons. They possess a crust, likely only a few centimeters thick, made of extremely compressed but ordinary matter locked into a solid, crystalline state. The star's magnetic field permeates this crust and extends far into space. In some neutron stars, this field is exceptionally strong, up to a quadrillion times more powerful than the Sun's. These ultramagnetic neutron stars are called magnetars. They're relatively rare. Perhaps only 10% of all neutron stars form as magnetars. Their lives are short because such intense magnetic fields act as a brake, slowing the star's rotation. Since rotation helps sustain the magnetic field, the field weakens as the star spins down. But while they exist, magnetars rank among the most captivating objects in the universe. With great power comes great responsibility. And if your cosmic duty is to be one of the most terrifying objects in existence, neutron stars certainly qualify. Why? Because in a neutron star, the crust and magnetic field are tightly coupled. Changes in one directly affect the other. The crust is under enormous stress due to intense gravity and rapid rotation. If its structure shifts, it can crack, triggering a starquake, analogous to an earthquake, but vastly more powerful. On Earth, earthquakes release tremendous energy as tectonic plates shift and fracture, enough to level cities and move mountains. In a neutron star, the effect is multiplied exponentially. Remember, the crust is incredibly dense, and surface gravity is immense. If the crust cracks and shifts by just 1 centimeter, the energy released defies imagination. This energy erupts as a colossal explosion in the crust, violently shaking both the surface and the magnetic field, whose reaction is, to put it mildly, catastrophic. When the sun's magnetic field is disturbed, we see solar flares equivalent to billions of nuclear bombs. But a magnetar eruption dwarfs even that. It can be trillions of times more powerful. In a fraction of a second, a magnetar can release more energy than the sun emits in 250,000 years. In 2004, astronomers were stunned when a massive burst of X-rays struck orbiting satellites. NASA's SWIFT satellite, though not pointed at the source, was overwhelmed. The X-rays penetrated its side with such intensity that the instrument, designed to detect powerful X-ray sources, was temporarily blinded. The source was quickly identified as a magnetar named SGR 1806-20, and its effects were astonishing. It actually compressed Earth's magnetic field and partially ionized the upper atmosphere. Remarkably, this magnetar lies 50,000 light-years away, on the opposite side of the Milky Way. The fact that an event 500 quadrillion kilometers distant could outshine a solar eruption is nothing short of extraordinary. The good news for those concerned about cosmic threats is that magnetars in our galaxy are extremely rare, likely fewer than a dozen. Moreover, such catastrophic eruptions occur very infrequently. Had one happened at any point in the last 40 years, our observatories would have detected it. And frankly, it's fortunate that Earth-orbiting astronomical satellites exist to study these phenomena in detail. Since their discovery, our understanding of neutron stars has deepened significantly. Yet, despite these advances, much about their nature remains beyond our comprehension. The more we learn, the clearer it becomes that they are far stranger and more mysterious than we ever imagined. Still, astonishing as they are, neutron stars aren't the most incredible objects in the universe. Not even close. That distinction belongs unequivocally to another product of supernova explosions: black holes. Stay tuned for more. In summary, we've learned that when a star with 8 to 20 solar masses explodes as a supernova, its core collapses to form a neutron star. These objects are characterized by extreme density, rapid rotation, and immensely powerful magnetic fields. Some manifest as pulsars, emitting bright flashes of light as they spin. The most magnetic among them are magnetars, capable of releasing colossal energy bursts detectable across vast cosmic distances.